Hey there, you. Welcome back to another deep dive.
Great to be here.
Today we're diving into a world that's, well, absolutely critical for modern manufacturing, but often kind of hidden in plain sight.
That's right. We're talking industrial cutting tools.
Specifically, those small but really mighty replaceable inserts. The ones used in turning metal parts. We've got some great sources lined up looking at how these inserts evolved and really zeroing in on one crucial thing: why their shape is just everything.
It really is fundamental.
So our mission in this deep dive, let's extract the core insights. How do different shapes enable specific machining jobs? How do they boost efficiency?
And ultimately how they impact cost and quality. Big impact.
Exactly. We want to unpack how these, seemingly small design choices lead to pretty big results out on the shop floor.
Absolutely. And to really get the significance of today's shapes, we probably need to go back a bit. Look at the history.
Okay, where do we start?
Well, the whole idea of using mechanically clamped, replaceable carbide inserts that really started taking off in the late 1950s.
Before that, it was different.
Yeah, before that, tools were often solid pieces. You had to resharpen them constantly, time-consuming, limited their life.
So this shift to a replaceable tip was like a really big deal then.
Huge. Absolutely huge. Initially, these early clamped inserts, sometimes people call them throwaway inserts.
Throwaway, just use and toss.
Pretty much use it, wear it out, discard it. But the tech evolved, pretty quickly. It allowed for much more complex forms.
Okay.
And that led to a really crucial change in how we think about them and even name them today. Indexable insert.
Indexable, right.
Yeah, that term highlights the ability to rotate or index the insert, bring a fresh, unused cutting edge into play.
So you're not just replacing a worn tip, you're getting multiple cuts from one piece.
Exactly. Multiple edges from a single piece of material before you need a whole new insert.
So indexable means multi-use, not single use. That fundamentally changes the economics, doesn't it?
Totally. Absolutely. And that economic driver, plus the need for, better performance, that's really pushed the evolution of insert shapes and surfaces. It's based on sort of three main design targets.
Okay, what are they?
First, you need optimum cutting geometry for effective chip formation.
Chip formation. That sounds technical.
It just means designing the face so the metal shears off cleanly and breaks into manageable chips. Vital for a clean cut, prevents nasty buildup.
Okay, controlling the chips. Never thought about that being a design goal. What else?
Second is creating intelligent outer shapes. You want to maximize the range of applications for that one insert. How versatile can this shape be?
Right, get more mileage out of it.
And the third is, the rational, sustainable use of the cutting material itself, making sure you get the most cutting edges or the best performance from these often expensive materials. Cost efficiency, basically.
Wow. So they're juggling chip control, versatility, and material cost, all in one tiny little component. Sounds like a real balancing act.
It absolutely is. And if you look at the market, you see this incredible variety of shapes. Squares, rounds, octagons.
Rhombics, trigons, even weird curvy ones. It seems like they've covered every possible shape.
You'd think so, wouldn't you? You might look at all that diversity and think, surely they've explored every geometric possibility, that the field must be nearing, saturation.
Yeah, it certainly feels like they've tried every angle.
Yet, the source material really highlights that tool manufacturers, they don't see it that way at all, not even close.
Really?
Yeah, they're constantly innovating, either introducing entirely new geometries or, just as importantly, finding new ways to use existing well-known shapes, what some call canonical configurations.
Like finding new tricks for old shapes.
Exactly. It's this continuous search for the ideal compromise between those core design targets we just talked about.
So innovation isn't just about a shape we've never seen before. It's also about getting smarter with the shapes we already have.
Precisely. Optimization is just as key as novelty. Okay, so let's maybe unpack this with some specific examples from the source material. See how these shapes actually work in the real world.
Great idea. Where should we start? Which shape?
Let's start with one that seems simple but offers some pretty significant advantages. The Pentagon.
A pentagon.
Yeah, ISCAR, for instance, they developed the POMG insert. It's a double-sided pentagonal carbide insert.
Double-sided.
Its regular pentagon shape, combined with being reversible, immediately gives you 10 indexable cutting edges, 5 on top, 5 on the bottom.
10 edges on one small insert. Wow. That's a massive number of uses before you need to replace it. That
Yeah.
must be huge for cost effectiveness, right?
Exactly. That's a key driver right there, getting that many working edges from one piece of carbide. Big cost saver. But how it's held is just as critical.
How so?
It has these specially shaped side surfaces. They're designed to fit perfectly into a dovetail profile pocket in the tool body, creates an extremely rigid clamping mechanism.
And why is that rigidity so important? What does that do?
Well, turning involves significant forces, right? Any instability, any wiggle can lead to chatter, poor surface finish, shorter tool life. It's bad news.
Gotcha.
So this secure clamping, it's part of their Dove IQ Turn family. It ensures the insert stays exactly put, even under really heavy loads.
Okay, so it's got tons of edges, held super securely, but how does the shape itself make it versatile?
Well, this single pentagon shape is surprisingly versatile because it's designed to work really well with two different tool types, which means two different entering angles.
Entering angle. That's the angle it hits the workpiece.
Basically, yeah, the angle between the cutting edge and the workpiece surface. So you can use this insert with a tool giving you a 55-degree entering angle. That's pretty standard for roughing to semi-finished jobs, deeper cuts, maybe up to 5 millimeters. Or, and this is where the shape's adaptability gets really interesting, you can use it with a tool providing a much shallower angle, 14.5 degrees.
And 14.5 degrees. That's really shallow. What kind of machining is that for?
That's perfect for high feed turning, where you take much shallower cuts, maybe up to 1.5 millimeters, but at extremely fast feed rates, zooming along.
Whoa! So one insert, one pentagon, handles both deep, slower roughing and fast, shallow, high feed stuff.
That's it. That's the versatility.
That is impressive for one shape. And you mentioned earlier chip formation and surface finish were goals. How does the Pentagon handle that?
Okay, look closely at the corner design on this one. It's got a radius, right? But it's flanked by two little wiper flats.
Wiper flat.
Yeah, they're not just for looks. Their purpose is to actually improve the surface finish on the workpiece. So even when you're doing heavy roughing at high feeds jobs where you'd normally expect a pretty rough finish, those wiper flats help smooth out the surface left behind.
Wait, so you get the speed and material removal of roughing plus a better surface finish at the same time. That feels counterintuitive.
It really does. And that's a key advantage the Pentagon shape, with its specific features, offers. It all comes together. Makes the POMG highly economical, 10 edges, remember, versatile across different methods, durable, and ultimately offers significant cost reduction, especially in roughing.
Okay, the Pentagon clearly rocks for cost and versatile roughing or high feed work. What about shapes designed for maybe different kinds of challenges?
Right. Let's turn our attention to the concave hexagon.
Concave hexagon. Okay, it sounds interesting.
This shape tends to excel in a different area. It's mainly about expanding the effective cutting range of the insert, and it's excellent for machining hard-to-reach spots.
It's hard to reach, like complex parts.
Exactly. And its inherent symmetry makes it perfectly suited for multi-directional cutting.
Multi-directional cutting, you mean like cutting forwards, backwards, sideways, all without swapping the tool?
Precisely that, yeah. It means the insert has to handle cutting forces coming from multiple angles, often in complex paths like profiling or contouring.
Right. Tricky stuff.
Which is why this concave hexagon shape is used for inserts like the Q6 M&MG and ISCAR's quick turn tools. These are specifically designed for demanding multi-directional jobs, often involving pretty heavy roughing loads.
Okay, under those constantly changing forces, how does an insert like that stay perfectly stable? Must be a challenge.
Good question. The Q6 insert, it has 3 stabilizing ridges on both the top and bottom surfaces. Yeah, little raised ridges. These fit securely into matching grooves in the insert pocket inside the tool body. That ensures a fixed position, really robust stability no matter which way you're cutting.
Cutter.
And crucially, the source points out, these ridges are on the rake faces, the surface the chip flows over, but they're designed so they don't block the chip flow. Essential for preventing chip jams and keeping the cut clean.
Ah, that's a smart detail. Adds stability without causing other problems.
Yeah.
What's fascinating here is how one basic shape, this concave hexagon, can be adapted. You mentioned it's used in other tools too.
Yes, exactly. It demonstrates the versatility of the core shape concept. The concave hexagon also shows up in the QuickK TLOCK tool family with the Q3 MCMT insert.
Okay, Q3.
Now, while it shares that concave hexagon form, it's actually quite different from the Q6 in some significant ways.
How so? Is it also double-sided like the Q6?
No, the Q3 is a one-sided insert, so it gives you 3 cutting edges. compared to the Q6. Well, the Q6 is double-sided, so assuming 6 points per side, that'd be 12 edges.
Okay, 3 versus potentially 12. Big difference. What else?
The main difference is its geometry profile. The Q3 has what's called a positive structure.
Positive structure.
It means its side faces are inclined and the bottom surface is smaller than the top. Think of it like leaning inwards slightly. The Q6, in contrast, has a more negative profile, more upright or even undercut sides.
And what's the benefit of that positive geometry in the Q3? What does that do?
Well, a positive geometry typically gives you a more positive cutting angle, which results in lighter, smoother cuts, less force needed.
Ah.
This makes the Q3 better suited for more precise work, lighter applications, finishing passes. Plus, those inclined sides give better clearance, better access when you're machining close to shoulders or trying to get into tight, hard-to-reach areas compared to a negative profile.
So the same fundamental concave hexagon shape, it can be engineered for heavy multidirectional roughing with the Q6 and for lighter, more precise multidirectional cuts with the Q3. That's quite a range from one starting shape.
It really is. It shows that, while the basic shape gives you a starting point, it's the detailed engineering making it single or double-sided, tweaking the profile from negative to positive, refining features like those ridges that really tailors the shape for specific tasks and performance needs.
Okay, this makes a lot of sense. Seeing how these specialized shapes offer very distinct advantages. But let me step back for a second. We've talked about squares, rounds, rhombics, pentagons, hexagons. I mean, there's such an incredible diversity. For a manufacturing shop, how do you even manage all this? Do you need a unique, dedicated tool body designed specifically for every single insert shape you might want to use? That sounds like an inventory nightmare. And expensive.
You've absolutely hit on a critical challenge in metalworking. Traditionally, yeah, you're right. The insert pocket, the part of the tool body where the insert actually sits, is very precisely shaped to match the specific contour of the insert it holds.
So one pocket, one shape, basically.
Pretty much. While there might be a few exceptions, maybe some similar shapes fit, generally each distinct insert geometry needs its own dedicated pocket design in the tool body itself.
Which means loads of different, potentially very expensive tool bodies just sitting on shelves waiting.
Exactly. And that's where this really elegant solution described in the source comes into play, using exchangeable cartridges. Cartridges that mount into a standard tool body.
Cartridges, you mean like a modular system, like swapping pieces out?
Precisely. That's a great way to think about it. Instead of the main tool body having that specialized pocket machined permanently into it, it has a standardized interface, a slot or mount, and that accepts these cartridges.
Okay.
Each cartridge, then, contains the actual pocket specifically designed for one particular insert shape. So the main tool body stays the same, and you just swap the cartridge to use a different insert shape.
Okay, wow. That immediately tackles the inventory problem for the tool bodies, right?
Yeah.
You need fewer main bodies.
Yeah.
And you stock a range of less expensive cartridges for the shapes you actually need.
Exactly. And there's another huge benefit. It provides this crucial layer of protection.
Protection? How?
Think about it. If the insert, or maybe its pocket, gets damaged during machining, which, it happens.
Crashes, extreme wear.
Yeah, unfortunately. It's typically the pocket within the cartridge that takes the hit. The expensive main tool body. Usually unharmed, you just replace the relatively low-cost damaged cartridge, not the whole tool assembly.
Oh, that is brilliant. That saves the really expensive part. That adds a lot of resilience to the whole system, doesn't it?
It absolutely does. It makes a huge difference to the bottom line and uptime. ISCAR's Serum turning tools, they're a good example of this concept in practice. The tool bodies accept these exchangeable cartridges.
And what kinds of inserts can these cartridges handle in that Serum turn system? Is it limited?
According to the source, the cartridges in this system are designed to hold a range of inserts, including rhombic shapes and round shapes. But what's really notable is they can be used with inserts made from all sorts of high-performance materials.
Like what?
Standard cemented carbides, obviously, but also the more advanced stuff. Ceramics, cubic boron, nitride, CBN, and even inserts tipped with polycrystalline diamond, PCD.
Wow, so really high-tech materials.
Yeah. And there's even an option for putting a separate little carbide seat within the cartridge for extra stability, especially for those harder materials.
So this cartridge system, it's not just about handling different shapes, but it also lets you use very different, highly specialized materials all within the same basic tool body platform.
Correct. That's a key advantage. And the CRM turn system adds features to support those materials too, especially the more brittle ones like ceramics and CBN.
Such as?
Well, it includes high-pressure coolant outlets directed precisely right at the cutting edge. And you can adjust them. That's critical for managing heat and chip flow with those tougher materials.
Right. Cooling is key.
And it also features an enhanced clamping mechanism, specifically designed to stop brittle inserts from rotating or breaking under load, helps ensure performance, and extends their life. If you connect this to the bigger picture, this whole cartridge approach, it completely changes the game for managing your tooling inventory, protecting your tool body assets, and expanding the range of materials and jobs a single tool body can handle.
It really does sound like it. Makes your whole setup much more flexible, cost-effective, and robust, less likely to break down.
Definitely.
So wrapping up this deep dive then, I think the really clear takeaway is that the shape of an indexable cutting insert, it's anything but accidental or cosmetic.
Not at all. It's the result of precise engineering, driven by balancing that chip control, application versatility, and cost efficiency for very specific machining tasks.
And even though there might be, a finite number of basic geometric forms, squares, circles, triangles, etc., the innovation just keeps going.
Absolutely. Manufacturers are constantly refining existing shapes, finding new ways to apply them, even for profiles that have been around ages, like the pentagon or that concave hexagon we discussed, always pushing the boundaries of what's possible in metal cutting.
It really underscores the sheer ingenuity packed into these tiny, critical components of manufacturing.
Yeah.
It's like a prime example of form-following function in the pretty demanding world of metal cutting tools.
Well said, indeed.
And, this raises an important question for you, the listener, to consider. Given the clear advantages we've seen today from specialized shapes like the pentagon for cost savings or the concave hexagon for multi-directional work, where do you think the next significant breakthrough in insert geometry will come from? What specific, maybe currently difficult machining challenge do you think that new shape will be designed to solve?
That's a good one to think about. What's the next problem geometry will solve?
Exactly. Something to mull over as you look at all the precision metal parts around you. Thanks so much for joining us for this deep dive into cutting insert shapes.
Yeah, thanks for tuning in.
We hope you enjoyed exploring this topic with us. Keep exploring the world around you.